It's also old.
Okay, guys, so you got to pay attention to this, okay? So this is a little bit above intermediate level, but it's kind of towards senior. Quadratic reciprocity, okay? So, and if you look at like that old guy from IMO, like the Jeff Smith guy, the old guy, his website, is like, what should I learn to prepare for IMO, right? And like back then, it's like literally nothing in the syllabus. But even then, he was like, Pell's equation, quadratic reciprocity, inequalities. Like he names like three things, right? And this is the quadratic reciprocity we want to talk about. So it's modular arithmetic. And what is it?
But what are the three things you said to learn? Gauss equation, quadratic reciprocity, and something else.
Inequalities.
I'll learn those things or something. Damn, that's crazy.
You take anyone's advice but mine, I see.
I take your advice, sir.
Okay, anyway, so basically, what is the law of quadratic reciprocity? If you do modular arithmetic, it's a question of determining when something's a square or not. Mod. Let's do a mod of prime, but there's ways around the prime, but we don't talk about that here. Okay, so this is called the Legendre symbol, okay? So if you have n over p, and let's just say p is prime for our...
I know the Legendre.
So this is Legendre symbol, okay?
Michael, can we get some drink?
Yes.
Oh, yes. Legendre.
So Legendre symbol, and what it does is it tells you whether n is a square mod p or not, okay? So output's 1 if n's a square mod p. So if n equals like something squared mod p for some x, yeah?
Can we drink the drink?
Oh, you're so dumb, be quiet.
Good question.
And it's -1 otherwise, but it's kind of like this other thing with 0 if n is a multiple of p, yeah? So if n equals 0 mod p, okay? You're just so spastic. I don't know, like...
Not bad, sir.
Right, so
I am not bad. Sorry.
this is not a square, yeah? This n is not a square mod p. Okay? So a lot of the time, knowing whether things are square mod p is really helpful. Remember like those times when you do like mod 4 proofs, and like squares are always like 1 or 0 mod 4, and that solves it?
Oh.
Well, this is... Okay, so the 4 is not a prime, but a lot of it suffices to look at primes, okay? And the law of quadratic reciprocity. So I'll give you the statement, and then I'll kind of do some prelims, and then give you the proof, okay? And it's a Combi proof, okay? So what is the law of quadratic reciprocity? So it tells you how to evaluate this symbol, essentially. So law of quadratic reciprocity, and just beware of abbreviations when you're crossing language barriers. So if you have two primes p over q, yeah, and you have the Legendre symbols, yeah, then it equals -1 to the power of p minus 1 on 2 times q minus 1 on 2. Okay. And how does this help you evaluate the symbol? Well, it's actually very nice. Like for example, if you have like say like 17, and you want to know if 3 is a square. No, if you want to know if 3 is a square of 17, yeah. If you guys are not listening, I'm just gonna skip all this because I kind of just want to teach people who care. So if whether 3 is a square of mod 17 or not, by this reciprocity, what you can do is you can flip it. Okay. It equals to whether it's 17 is a square mod 3 or not.
Oh, yeah.
Up to this sign change, right? And so p minus 1, so if 3 minus 1 is 2 on 2, so that's just -1, right? And 17 minus 1 on 2 is just 8, so the whole thing is +1, so there's no sign change, yeah?
Yeah.
And then to do 17 mod 3, it's just this, because 17 is equal to 2 mod 3, right? And then it's easy to know whether 2 is a square mod 3, yeah? And it's not, okay? So the squares mod 3 are all 1 and 0, yeah? Okay. Okay. Alright. So to prove this, And actually, there's other things which should really be known as well. So this Euler's criteria. And I'm gonna go through this quickly. So if you're not gonna ask questions, I'm just gonna keep on this pace. Okay. Yeah. So I'm talking to everyone. So Euler's criteria says the Legendre symbol over p, yeah, is equal to a to the power of p minus 1 on 2 mod p. Okay. Does that make sense? So that's one way to kind of evaluate the Legendre symbol directly. Yeah. Just take a big power of the thing that's in the symbol. Okay. All right. So why is this true? Okay.
Fermat's little theorem for if it's square.
Yeah. So by Fermat's little theorem, if a is a multiple of p, then obviously both of these are 0. Yeah. So we only have to consider the case where it's plus or minus 1. Okay. But by Fermat's little theorem, if a is not 0, then a to the p minus 1 is equal to 1, right? Mod p. That's Fermat's little theorem. Okay. And so if you have a p over minus 1 on 2, that's like the square root of that, yeah? But it's not the square root, it's a square root, yeah? There's 2 square roots. So a to the p minus 1 on 2 is either 1 or minus 1, yeah?
Yeah.
Because it has to square to 1. Okay? Okay, but then the question is, why is it 1 and when it's a square and minus 1 when it's not a square? Well, if a is a square, right, so a equals x squared, yeah? Actually, let's not use x, let's use b. If a is b squared, yeah? Then a to the p minus 1 on 2 is equal to b squared to the p minus 1 on 2, right? Which is equal to b to the p minus 1, yeah? Which is equal to 1, yeah? So that's why if a is a square, it equals 1, okay? But, okay, all the squares have to output 1, okay? And there's a lot of squares, okay? So all the squares satisfy this equation, okay? Equals 1, yeah?
Yeah.
But that's a polynomial equation, okay? So it can only be satisfied by p minus 1 on 2 things.
And there's only a maximum of p minus 1 on 2 squares.
Exactly, because the squaring function is exactly 2 to 1, right? When you exclude 0. So there's only half the things are squares. So that means all the other half, the non-squares, have to give out minus 1.
Yeah.
Okay? Alright, that's Euler's criteria done, okay? If you want to ask questions, you better ask questions, because I ain't stopping.
I got it, sir.
Okay, good. Okay, and now that this is getting tougher, okay? So Chinese remainder theorem. So there's the baby version of the Chinese remainder theorem, and this is the adult version of the Chinese remainder theorem. Okay?
What happened to the toddlers?
Okay, so the modern version of the Chinese remainder theorem is, so if you look at the set of integers mod let's just do p and q, pq, yeah? Right? And then you look at the set of integers mod p paired with the set of integers mod q, okay? Yeah? Okay. There's a function that takes this set to this set, okay? And it's defined by, if you have an integer x, so if you have a number x mod q, pq, yeah, right? Then you take that number mod p, and then you take a mod q, and you make that pair, okay? Okay, that's super annoying. So, like, for example, if p was like 3 and q was like 5, right? So pq is like 15, yeah? You would take like the number 14, okay? Yeah. And you'd map it to like, what's 14 mod 3? It's like 2, right?
2
and what's 14 mod 5? It's 4. So that's how the functions are defined, okay?
Yeah.
And the crazy thing is about this function is it's a bijection, okay?
It's Chinese remainder theorem. Because
Yeah, so the fact that it's a bijection is called the Chinese remainder theorem. Okay? So, you can see why it's the Chinese remainder theorem in the sense that, like, so Chinese remainder theorem basically says if you have an equation x equals 2 mod 3, right? X equals 4 mod 5. Then there's a unique solution x equals something mod 15, yeah? Yeah?
Yeah.
So that's exactly saying that this is a bijection. Because there is a solution is saying it's surjective, and if the solution is unique, is saying it's injective.
Yeah.
What is subjective?
Oh my gosh. So surjective means
1-to-1.
everything in this set has something from the
bijection,
input that
right?
is sent there. Yeah.
But everything is like included in the other one.
So every thing in this set is output by the function.
Oh, okay.
Okay. Yeah. So I think the only reason I had that reaction is because I think I've mentioned what surjective was previously. Yeah.
You have.
Okay. So that's the Chinese remainder theorem. Okay. And what's more, you can actually define multiplication and addition on these sets, right? So the multiplication here is just obviously like, it's just modular arithmetic, yeah? It's literally just timesing stuff and modding 15, yeah?
Yeah.
So it's literally the multiplication and addition from modular arithmetic, yeah? Here, the multiplication and addition come from the modular arithmetic. What are you even looking at? Anyway, so it's like, it comes from the modular arithmetic, and then you just do it separately on each entry, yeah? So for example, if I have 2, 4 here, and I want to add it to 3, 5, yeah? Then I just get 2 plus 3, 4 plus 5, yeah? And if I want to times it by 3, 5, yeah? Then I get 2 times 3 and 4 times 5, yeah? So it's the most trivial way to make a multiplication and addition when you have a product, okay? Okay. Alright. So we can even say more, okay, and still call it the Chinese remainder theorem. We can say this bijection is not just a bijection, but it's actually additive and multiplicative. Okay?
Yeah.
So, and the multiplication distributes over the addition, and when that happens, you call the set a ring. Okay? Alright? So this is a function between two rings, and when it preserves all the properties, you call it a ring isomorphism. Okay? So that's literally, all these words are just there to say the things that I've already said. Okay? It's a bijection, it's additive, and it's multiplicative. Okay? Yeah, but that makes it more obvious why, like, if we take this set, okay? If we take this set, the Z mod PQ, okay? And put the little cross on top to denote the invertible things. You know what invertible means? Invertible is like, there's a reciprocal. So you can times by something to get 1.
Oh.
Yeah?
Wait, that's everything.
Wait, it's a
No,
ring, so
because
it's
P
invertible, right?
is not invertible, right?
Oh.
It's PQ, yeah?
Yeah.
So in modular arithmetic, like if you have if P is 2 and Q is 3, that's like 6, right?
Yeah.
Like mod 6, 2 is not invertible, yeah? Does that make sense? Like mod 6, 2 is not invertible, because if 2 is invertible, yeah, then you times both sides by 3, and you get 0 equals 3, right?
Yeah.
Mod 6, which is not true, yeah? So not everything's invertible, okay? So these are the invertible things, okay? Okay, and the claim is if you restrict the function to the invertible things, it's still a bijection, okay?
Oh yeah.
Oh, it's possible.
Okay, and that basically follows from it being multiplicative, yeah? Because what happens is, like, if you have something that's invertible, right? So that there's like, if A is invertible, it means there's like a B such that AB equals 1, right? Okay. But then when you take the function, so we can check that f of 1 goes to 1, right?
Yeah.
Because 1 is literally just 1 comma 1, yeah? Because 1 comma 1 times everything to keep them the same, yeah? Okay, so f of 1 equals 1 comma 1. So when you do multiplicative on this, you get f of A times f of B equals 1, 1, right? And so f of a is obviously invertible because its inverse is f of b. Yeah. Yeah, and why is it so? If so, I guess that's saying that f of a is in the invertible things in here, right?
Yeah.
Okay, but then why is the invertible things in the product the product of the invertible things? Well, that's kind of obvious as well. Like if you have like a C and a D, right? Like for that to be invertible, you need like an E and an F, such that that equals 1, 1, right?
Yeah.
And so the C times with the E and the D times with the F to get 1, 1. And so the CE individually equals 1 and the DF individually equals 1, right? So then this is just the invertible things separately. Okay? And Andy is gone. Disqualified himself. Okay, so now we have a bijection from here. So actually, you also know the number of invertible things. Okay, so the fact that this is an injective, you already know it's a bijection. Okay, because the number of invertible things in modular arithmetic is given by Euler's phi function, right? So the size of this is given by 5pq. Yeah. And remember, 5pq is just 5p times 5q, right?
Yeah.
And this is literally 5p, and this is 5q.
That's 5pq.
And 5p is just p minus 1, yeah?
Yeah.
There's only one thing that's not invertible mod p. Yeah, so sometimes it helps to look and listen, okay? If you're only listening or only looking, you're missing information. Because I'm not just saying it, I'm writing it, and I'm making like facial expressions. I don't know what's on your computer, but this is not going to be easy for you, okay?
Sir is making a lot of sense. You should listen, Andy.
Okay, so...
He's making sense, though.
Okay. And so the claim is, okay, with this function, okay? So this function is essentially, this setup is summarizes the Chinese remainder theorem, okay?
Yeah.
So, you know, like modern maths, the claim is you can express everything as function, okay? So this expresses the Chinese remainder theorem as a function, okay? So trig is expressing, you know, triangles as functions. We're going to use this function to prove the law of quadratic reciprocity, okay? Alright. That makes sense? So let's call this function g, okay? Alright. So I want to look at 3 subsets of this set here, okay? Alright. I want to look at 3 subsets, okay? The first subset here is so one of them was you have 1, 2, 3, and you go halfway along the set. So you, instead of going all the way to p, you go to p minus 1 and 2, okay? Okay, and then we call this number capital P for shorthand, okay? And we take that set, we take the
And multiply it by...
and these are all invertible, so we don't need to put like a cross on it, yeah?
Yes.
And we take the product of this set with
The set 1 to q.
the whole set here.
Yeah.
Okay? Yeah. So basically we have a product of 2 sets, but we cut the first set in half. Okay?
Okay.
Alright. The second thing is exactly the same as the first thing, but the symmetric counterpart of it. So we have this set, okay? Finding it hard to jump back in here. Need to ask some questions. So this set, and now we have 1, 2, 3 to q minus 1 on 2. Okay, and we'll call this capital Q. Alright? Okay. And the whole point of these sets is that it has the property that every element of the whole set, so this is literally half of the whole set. So every element in this whole set, either it's in this subset or its negative is in this subset. Does that make sense? So what's a typical thing in this set? You know, like it could be like So if it's 3 and 5, right, the number could be like 2, 4. Yeah? Okay, well 2, 4, the 2 is more than halfway, right? So the 2 is actually -1, yeah? Right? So it's -1, and 5 is also past halfway. Okay. So 2, 4 is actually the same as so it's also the same as -1, -1. Yeah.
Yeah.
Okay. So can you see 2, 4 is not in the first set, right? Because 2 is past halfway, yeah? P minus 1 on 2 is 1, yeah?
Yeah.
Okay. But if you take the negative of 2, 4, it's just 1, 1, right?
Yeah.
And 1, 1 is in this set, yeah?
Yeah.
So the point is, for every pair of things, either it's in the set or the negative is in the set, okay? And negatives is half, right? So that's why these are half of the set, yeah? Okay. 3 is,
You take half of
so we're taking half of this set here, right? And then we're importing it to this side using the function, okay? So what we would do is we take the set, so we go from 1, 2, 3, all the way up to
PQ minus 1 on 2.
yeah, so PQ minus 1 on 2, okay? But we only want the invertible ones, okay? Because we only have invertible things, yeah? Okay. And we want to take the image of that under the function, so these are actually pairs.
Yeah.
Okay. Okay. That makes sense? So there's nothing to really make sense right now. It's just 3 definitions, okay?
That makes a lot of sense.
Okay, and the claim is the definitions have these properties that they're subsets of the codomain, okay, that have the property that either, for everything in the codomain, every x in the codomain, either x or minus x is in each subset, yeah?
Yeah.
Okay. Okay, so now what we want to do is we want to multiply everything together, okay? So we want to multiply everything together, and we're going to get 3 different products. So everything from 1, everything from 2, and everything from 3, okay? Does that make sense?
Yeah.
So how do we multiply this together? Well, can you see that? So this set here, okay, this is just a set of 1 to q minus 1, okay? So if we're multiplying all the pairs together, right? Yeah. Can you see there's like q minus 1 things for each? So the things in this set are like 1, 1,
Yeah.
1, 2, 1, 3, right? So there's a 1, something for every something from 1 to q minus 1.
Yeah.
Okay. So you're basically timesing every one of these numbers to the power of q minus 1, right?
Yeah.
So then when you take the product, you get p minus 1. So capital P is a p minus 1 2 is a capital P factorial, yeah,
Yeah.
to the power of q minus 1, yeah, comma, and then on the other side it's q minus 1 factorial to the power of p, yeah.
Yeah.
Okay. Does that make sense? You're just timesing all those pairs together, okay? And the multiplication is defined entry-wise, so you're just timesing them separately, okay? So you just literally, for the first entry here, you're just timesing all these 1 to p minus 1 on 2's together, okay?
Oh, yeah.
That's where you get the factorial.
And there's q minus
But
1 of them.
but they're paired with lots of different things, so they're gonna keep timesing, okay?
Oh, yeah, I get this. This makes sense.
Okay, so if you understood that, then the number 2 is exactly the same thing,
Yeah,
okay? It's just q and p swapped, okay? The number 2 is q factorial to the power of p minus 1, yeah? Don't distract Andy. He's actually focusing. So he needs to sprint and catch up the distance he missed from not concentrating at the start. Okay. So if you might also notice that q minus 1 factorial mod q is minus 1 by Wilson's theorem, but we don't need that, okay? I don't think we need that. I think it should just cancel. This is to the power of q. Okay, does that make sense?
Yes.
Okay, so this next bit is a bit trickier, okay? So the next bit is a bit trickier, okay? So how do you get half of... So let me just give you an example. So p equals 3, q equals 5, yeah? So let's just count. So if you look at halfway, okay? You go 1, 2, 3, 4, 5, 6. So it's 15, right? So half of 15 is 7, yeah? So you stop at 7, yeah?
Yeah.
Okay. But you don't want 3 and 6 either, yeah?
Yeah.
Because they're divisible by they're not invertible, yeah? And you don't want 5 either because it's not invertible. Yeah. So you basically got 4 things that you want to times together. Yeah? Okay. So how do you times them together? Well, you're thinking of them as pairs, so you only need to do the mod q and mod p separately, right? So you only need to do mod p times them together. That's one of the answers. And then you do mod q and then times them together. That's the other answer. Okay. So let's have a look at this from the point of view of 3, mod p, yeah? So 3, if you do this mod 3, you get 1. Let me make the black. You get 1, yeah? 2, okay. So 3 is just reset at 0, yeah?
Yeah.
And you get 1 again, yeah? Okay. So, like, the point is, you get, you just keep going from 1, so you just keep going 1, 2, 1, 2, 1, 2.
Yeah.
Like, if q was bigger, you just keep going 1, 2, 1, 2, 1, 2, right? But you don't get the 1, 2 at the middle. The 1, 2 in the middle is cut in half. See how there's only a 1 here? There's no 2, right? Okay. So basically what you get is the 1, 2 is exactly p minus 1 factorial, yeah?
Yeah.
Okay. Yeah. And the 1 that's cut in half, yeah?
Yeah.
It's capital P factorial. Yeah? Does that make sense?
Yeah. What about the 7? Oh, the 7. The 7.
Wait,
Oh, wait, did I miss the 7?
hold up, what's going on here? No, I'm pretty sure it's like you just ignore the Q cover now.
Wait, so
Do
P
you
equals...
count 5 when you're doing 3 or not?
Oh, no, the 5 is deleted. Yeah.
You just ignore the Q and then get rid of it there.
Yeah, wait, what happened to 7?
Basically, like, 7's the one that's cut in half because of the end. Because it just ends.
Wait, wasn't 4 cut in the 1? 4 is the 1, right?
And then 4 is just because 5 got rid of because of the condition.
Yeah.
Like the invertible.
Oh, okay.
Like,
So
we just
4 is not cut off. So 5...
We just ignore that.
So the way we do this,
Deal
yeah.
with it later.
So we keep... So, yeah, so so Andy makes a good point. So, and Alex. So, you keep the 5 in there for now, right? You have 2, okay, and then the 7 is the one that's cut off, okay, it has a 1, yeah? So then what you get is you have a bunch of p minus 1 factorials and 1 p factorial, yeah? Okay, and then what you do is you divide out by the 5s, yeah? So you divide out by the multiples of q, yeah?
Yeah.
So in this case, there's only one multiple of q, yeah? But there's as many multiples of q as, because the whole thing goes up to pq minus 1 on 2, right? Yeah. So there should be So it should be p minus 1 on 2 multiples of q. Yeah? Does that make sense? Because p minus 1 on 2 times q is pq minus q on 2, right? And if you increase it by one more multiple of q, it'll be over this. Yeah? So that's capital P multiples of q. Yeah? So then there's q to the power of capital P, right? Yeah? But the multiples go like 1q, 2q, 3q, 4q, right? Up to pq. So then there's also a capital P factorial. Does that make sense? Okay. And yeah, so how many multiples of q are there? Well, there's capital P. How many multiples of p are there? There's capital Q, right? So that's why p minus 1 factorial is to the power of capital Q, right?
And the p minus 1 and the big P factorial is cancelled, right?
Yeah, so this you might have to watch the recording because we were going through this quite fast. So we get p minus 1 factorial to the power of q, and then the capital P factorial is cancelled, you see that? So then you get that over q to the p, right? That's if you did it mod p. Okay, so if you do it mod q, it's just the reverse, yeah? So q minus 1 factorial to the power of p over q to the power of, over p to the power of q. Okay. Okay, so all the hard work's been done now, okay?
Oh shit.
So this should be easier now.
Wait.
So basically now what happens is, so because these sets have the property that either x or minus x is in the set, right?
Yeah.
But not both, yeah? Exactly one of them is in the set. Then when you times them all together, then you're really just timesing all the x's together, but with all these plus or minus signs.
Yeah.
Right? So these three numbers differ by a sign. But otherwise they're the same number. Does that make sense? So these differ by like a plus or minus. What happened to the other one? I bought this drinks for you guys, and then my kids end up drinking all of it. Okay, so they differ by a sign, okay?
Yeah.
Okay, so if you think about it, if we know the signs, okay, then we get sort of some pretty useful information, right? Like we get kind of like two equations plus two equations on the left. Two equations on the left, two equations on the right, yeah?
Yeah.
Okay. And since I claimed that we don't need Wilson's theorem, like one of those equations is probably just going to be used to cancel out the p minus 1 factorial. Okay. Okay. The point is, I guess the point I'm trying to make is we don't need to know all the sign changes explicitly to get the information we want. Okay.
I think I understand, maybe.
Okay. Okay, so let me just explain how the sign change.
Wait,
So
I might understand.
okay, good.
What?
So I want to explain what the sign is that's changed from 1 to 2. Okay, and then I'm claiming that that's all I need to know to get the law of quadratic. So I don't even have to know the final sign change, but because I have sort of two entries to equate with the other things, I can actually use it to solve for the sign change. Okay, and still have enough information left over to get quadratic reciprocity. Okay. So what's the sign change from 1 to 2? Okay. So if you think about it, okay. So if you look at the sets 1 to 2,
Holy
okay.
crap, that's insane.
So
that's actually insane.
So there's a subset that goes from 1, 2, 3, all the way up to p minus 1 on 2. So that's capital P, yeah? Cross the set from 1, 2, 3, all the way up.
Need half, like some of the entries.
Yeah.
Do like one from each.
So go up to capital Q, yeah?
Yeah.
So if you take that subset, can you see that subset here is common to both 1 and 2? right? That's in both of them, yeah?
Yeah.
Because both of them have to have at least the first half in each factor, yeah?
Yeah.
That's a common subset. So
Yeah.
whatever they multiply to, it doesn't affect the sign change, right?
Yeah.
Because it's the same in both.
Yeah.
So if you want to calculate the sign change, you can just ignore that, okay?
So it's only the ones from
Yeah. So if you ignore that set, okay, then what's left in each of them, okay?
the ones from P minus 1 to
So if
This
you
is actually crazy, man. This is actually crazy.
yeah, so if you ignore the first set, right?
Bro.
Okay. If you ignore the first set, and in some sense this video is like 3 years in the making, because it's the first time I actually talked about it was like 3 years ago to Haiping and Sing. Anyway, so if you ignore that set, okay, then what you get is you get the first half 1 to P, yeah, cross the second half of this, yeah, because the first half you deleted, yeah. So now it's 1 to P, capital P, cross essentially the second half. But the second half is a negative of the first half, right? You know why, right? Because it's modular arithmetic, yeah? So it's essentially 1 to capital P, and then it's minus 1 to minus capital Q.
Yeah.
Okay? So 1 becomes 1 all the way up to capital P, cross negative 1, negative 2, all the way up to negative capital Q. Okay? And the same thing happens for 2, okay? For 2, you get rid of the positive half, so you only have the negative half left for the P, okay? So 2 becomes minus 1, minus 2, all the way up to minus P, okay, cross 1, 2, all the way up to Q, okay? Yeah? And so can you see that everything in the set, the first set, is actually the negative of something in the second set?
Yeah.
Okay? So if you have a number like x, comma, negative y, right? Yeah?
Yeah.
Like, which corresponds, you know, it could be like 3 comma negative 4, yeah? That's not in this set, but negative 3 comma 4 is in this set, right?
Yeah.
So you can actually, there's a bijection from these two sets under the correspondence minus x to y, yeah?
Yeah.
Does that make sense?
Yeah.
So every element is the negative of some element in the other one, yeah?
Yeah.
So then the sign change happens exactly however many elements there are.
Yeah.
That makes sense? And so the
the
total number of elements here is capital P times capital Q, right?
Yeah.
So then the sign change is minus 1 to the power of capital P times capital Q.
Yeah.
Does that make sense? Okay. That's all we need now, okay? So this sign change here,
capital P and capital Q of P minus 1.
so this sign change is minus 1 to the power of PQ, okay? Okay, let me just show you how cool this is. So,
And that's
okay, so maybe something you weren't aware of as I'm saying it, but little p to the power of capital Q, yeah?
Yeah.
That is one of the terms in quadratic reciprocity, okay?
Yeah.
So that's something I could have pointed out earlier, but I was hoping you might notice. So p to the power of Q is p to the power of Q minus 1 on 2, right? Yeah? But remember, by Euler's criterion, that's Q over P, right? Yeah. Okay. And then that's Q over P mod P, yeah? Mod Q. What? Mod Q, yeah? I think it should be P over Q, right?
Yeah.
P over Q. Sorry.
and when you
P over Q. Okay. And the same thing, Q to the P equals Q to the P minus 1 on 2
P to the Q mod Q does P.
is equal to Q over P mod P. Yeah?
and when you multiply
So this is
the
Euler's criterion.
reciprocity,
Okay. Okay. And the cool thing about this, because the numbers are either 1 or minus 1, yeah? It doesn't actually matter if it's in the numerator or denominator, because 1 or minus 1 in the denominator is the same as in the numerator, right? So this term here is literally, you can write it as P minus 1 factorial to the power of capital Q times, and Q to the P we just said was this Q over P symbol, right? Okay. And then this is literally q minus 1 to the p. So there's no denominators, okay? And this is the other symbol, p over q. Yeah? And remember what we're trying to prove. We're trying to prove q over p times p over q equal to minus 1 to the pq, okay? So that's what we're trying to prove, yeah? Okay. So, okay, so let's have a look at 3. Let's equate 3 and 2, okay? Yeah? So if you equate 2 and 3, yeah? Okay, so we said 2 is the same as 3 up to a sign change, okay? So let's call the sign change like epsilon, okay? Or it's actually a sign. What's sign permutation? It's like sigma. Okay. So let's call the sign sigma, yeah?
Yeah.
So that means 1 equals sigma times 3, yeah? So 1 equals, or 2 equals sigma times 3. Sorry, 2 is related to 3. So 2 is p minus 1 factorial. And if you're equating the pairs, you just equate the entries, okay? So the first thing is p minus 1 factorial, okay, to the power of capital Q, okay? We don't need it. I already mentioned it. So p minus 1 factorial to the power of capital Q equals p minus 1 factorial. It cancels, right? To the power of capital Q, yeah? Times the Legendre symbol Q over p, yeah? But it's not necessarily equal, but it could be minus sign. So that's why we put a sigma here, yeah? And the good thing about minus sign, you can put it on either side of the equation, it's still the same, right? Okay. But notice here, you already get cancel, yeah?
Yeah.
And then Q over P is actually equal to the sigma, yeah? Yeah? So the sign change is actually equal to the Legendre symbol, okay? Alright. Let's do the same thing on the right side, yeah? So on the right side, you get q factorial to the, wait, why is it to the p minus 1? P minus 1. Okay, q factorial to the p minus 1 equals q minus 1 factorial to the capital P, p over q, right? And then times by sigma, yeah?
Yeah.
Okay. But sigma is just q over p, right?
Yeah.
So you get q factorial to the p minus 1, yeah?
Yeah.
Equals little q minus 1 factorial to the capital P times the left-hand side of the law of quadratic reciprocity, right? Yeah. Okay. Okay, so if you know Wilson's theorem, then you actually don't worry about the q minus 1 factorial that much, right?
Yeah.
But you don't actually need to know that. But the point is, you might just worry about the capital Q factorial, right? Okay. So how do you get the capital Q factorial? Well, that's where 1 comes in, right?
Yeah.
This is unnecessary.
Unnecessary.
Like you just
Is it already
compare
done?
straight to 1.
Compare what straight to 1?
I swear you just compare straight to 1.
Wait, you can't compare, like 1 and 2 are the same.
No, like you just I swear you do. But no, you just compare this guy to this guy and this guy to this guy.
Yeah, but that you need 1, 2, and 3, right?
Yeah, but you literally don't need these guys. Like they're just like
Yeah.
they're unnecessary.
Okay, so the point is, okay, so basically we just need to get rid of the capital Q factorial, right? But if you look at this, the capital Q factorial is related there, right?
Yeah.
Alright, let me draw in dark blue. So the capital Q factorial, yeah, is literally equal. So capital Q factorial to the power of p minus 1 is literally equal to, okay, q minus 1 factorial to the power of capital P, right? Yes?
Yeah.
Up to a sign change, but we already know the sign change is minus 1 to the PQ, right? Yes?
And that solves it.
Okay, and then this is equal to that, right? So this means that, you know what I'm talking about here?
Oh my god.
So if this is equal, then this,
It's equal to
that thing has to equal that, right?
Reciprocity.
Yeah.
Oh
So the one thing you got to be careful is that they're like equal mod either P or Q, right? But the thing is, these are just plus or minus ones, right? So if you conclude that's true mod P or mod Q, it's still true. You know what I'm talking about? So I should probably emphasize the second equation is gotten from the second entry, which is true mod Q, right? Yeah. And then we got this from 1 and 2 in the second entry, which is also mod Q.
Yeah.
Right? So the conclusion actually does hold mod Q. So we got the quadratic reciprocity, but we only got a mod Q, right?
But we can do the same thing with mod P, right?
Well, you don't need it because once you got a mod Q, like it's just plus or minus 1, right? So if something is so now we got P over Q, Q over P, you know? That's equal mod Q. You know? Yeah, because the point is, like, I think, so P and Q, we should assume them to be, like, odd or something, yeah? I think a lot of this argument is maybe needed to be not 2, okay?
Yeah.
So, when they're odd, so 1 is different from minus 1, right? So you can just tell the difference between 1 and minus 1. And all you have to do is tell the difference between 1 and minus 1 for this to be true, yeah? You know what I mean? So, this number here is either 1 or minus 1, and this number here is either 1 or minus 1, right?
Yeah.
And mod Q can tell the difference between that, yeah? And then obviously this number here is either plus or minus 1, right? So knowing it's true mod Q is enough to know it's just true. Does that make sense? Yeah.
Bruh.
Yeah, so it's kind of crazy, right? Like, when did Gauss prove quadratic reciprocity? When was Gauss around?
7. How would you think of this yourself, bro?
So Gauss,
So insane.
so Gauss proof. Well, when was Gauss around? So this is Gauss birth. 1777, right? So one of Gauss's claims to fame, you know, like Pascal proved Pascal's theorem when he was like 16 or something. Gauss proved law of quadratic reciprocity when he was 16. Okay. And he was so proud of it, okay, and he thought the theorem was so amazing that he kept coming up with new proofs, okay. So this, so what's 1777?
This guy had 1, 2, 3, 4, 5, 6 children. That's a lot of children.
Did they all survive? Because that's like that was the thing back then. Anyway, so such an insensitive question if you think about it. But they're all it's a long time ago now.
What is he siblings like?
So okay, so let's do the maths here. 1777, okay. 1777, yeah.
Yeah.
Plus 16. 1793, right?
Yeah.
So apparently, quadratic reciprocity was first proved in 1793, yeah? Right, so Euler's maybe a little bit before Gauss, yeah? And then there was like a lot of 1765 with all the circle things we did, right? 1793, okay? And this was not the proof, okay? So the original proof of quadratic reciprocity, no one would dare to teach high school students, okay? Because there's a Gauss Lemma, which is maybe not too hard, but it's long, okay? And it's kind of technical, but this is like purely Combi, and it's actually really nice, right? And you can all understand this, okay? And maybe if you don't, you can re-watch it over and over again.
I
Okay.
don't know. I don't know if Kurt would understand this.
Okay.
No, probably would not.
Okay, my video. Okay, so okay, so 1793. Okay, so that's like the first proof, right? Yeah. Then you keep going. There's like the fifth proof. Okay. I don't know exactly when the fifth proof was. Okay. But the fifth proof got adapted to something. Okay. And that got adapted to something else. And then someone also adapted that and then came up with this proof. Okay. This was. So I don't really know because the person who wrote the paper, they didn't attribute it like definitively to themselves, obviously, but there's this guy called Rousseau. He published actually in Australian Journal of Maths. Okay, like let's say 1989. Okay, it only got published in 91. Okay, so it kind of got changed so much by 1989. Okay, that's what the proof, what one of the proofs look like. Okay, so that's an amazing achievement because in some sense you had a theorem which really only made sense to be taught to people in uni. You can actually teach it in a math Olympiad curriculum, okay? Because it's literally a Combi proof of law of quadratic reciprocity.
Jesus.
Okay, and all you're really doing in this proof is you're timesing things by 1 or minus 1. Okay? So that's why it's Combi. You're just counting the ones or minus ones. And somehow you manage to conclude, because these are all just ones or minus ones, right? Okay.
It was understandable by high school students.
Yeah. So actually, not only is this proof understandable by high school students, it's getting to the point where it's derivable by high school students.
What?
Okay, that's how far we've come. Okay, so there's people
I don't know.
which I didn't really understand because I feel like when we submit research papers and the result is known, it doesn't get published, right?
Yeah.
But there are other people who are getting this repeat proof published, okay, and claiming to have come up with it independently, okay. So, yeah, but I guess maybe they were more likely to get accepted because they submitted it while they were in Harvard or something. I don't know.
I feel like the issue might be that what we submitted last time was like really.
Oh yeah.
Alright.
Okay, so times have changed. Okay, so before, like I think in Maths Olympiad before, you probably wouldn't even get taught the proof. You just get the statement and just some problems to solve, right? Now, and it was difficult, right? The proof is like introduction to number theory has a proof. The standard proof, has the Gauss Lemma, and then in Broken Bay we read the shortest ever proof or whatever. But it's not as memorable, right?
I swear this one can fit on one page.
This is more memorable,
I
right?
swear this one can fit on one page.
It depends on how much Chinese remainder theorem you write on that page. You know what I mean?
Like if you just write like
if you write CRT, then this can fit in the first the title. But if you write the full Chinese remainder theorem and explain everything, then it's maybe like a 2-page.
I swear this can fit on one LaTeX page though.
Yeah.
This
Yeah. So
the minimalist proof is slightly
yeah, the minimalist.
Slightly aids.
Yeah. So this is kind of what we're trying to go for. There's actually another number theory thing which is it's still outside the realm of high school, Dirichlet's theorem. Given A and B co-prime, there's infinitely many primes, which is A mod B. Sounds very simple, right? There's there's no known proof that's accessible to high school students.
Dirichlet's theorem.
But if you kind of know complex numbers and you're willing to accept certain things about limits, then you can actually prove Dirichlet's
What do
theorem.
you mean certain things about it?
So the exponential, the series expression for log and an exponential
theorem
complex.
Is for A and B co-prime, there are infinitely many primes of the form A plus XB.
Yeah, A mod B. Yeah.
Yeah.
But in Australian high school, they're teaching different integrals.
Yeah.
So surely you can understand.
So I tried, right, and then people they didn't quite hang on to the end. Let's just say.
Oh.
Were you there? Did you?
No.
It kind of started, with the other generation. It's a generation. 1 year's a generation with you guys, okay? Because that's the amount of advancement that happens. Alright, are there any questions about this?
Bruh, this is insane.
So I don't really know
This
who to
is
attribute it
also
to, but the point is the proof
Sorry.
has advanced. Yeah.
Oh my god. This just seems. I don't understand how someone would motivate
Yeah, like,
this.
either Russo is like insanely smart, like a friggin'
Well, I mean, so
500
I don't know
Yeah.
exactly what.
or
the
he randomly stumbled upon set 3 and he's like, oh shit.
No, I feel like a lot of these things were already known in like the fifth proof and the variations.
So Gauss was 500 IQ.
But so one thing that he does claim to get rid of is the Gauss lemma. So maybe that's what the innovation was. But also apparently people independently proving it while they're in high school. So it's maybe the sign of the times. You know how like I don't know, you're probably too young for this experience, but there's some theorems which like just based on your overall math maturity, you can just prove them. You know what I mean? Like prove like the quadratic formula. You know what I mean? Like that's something, at some point it was not possible to do for anyone, right? But now it's like anyone can kind of, with a certain amount of maturity, just figure out how to do that.
I feel like
You know what I mean? And I feel like this is kind of where that comes under now. It's getting to the point where like there are people, yourselves maybe included, that you can get to a point of maturity. Like if it was Gauss, maybe Gauss would be coming up with his first proof when he's 16, but if Gauss existed now, maybe he'd come up with this proof when he's 16, you know what I mean? Like,
his proof when he was like 12.
Bruh. How do you come across this set 3? Like, I swear he just had to have come across it randomly, and then, while doing something else, and thought, this looks like q to the p minus 1 over 2.
But how you?
yeah, but the crazy thing is you can't figure out, like, it's not easy to figure out the sign change to Q to set 3, right? But you don't need to, yeah.
But then this guy, like, somehow made some inspired construction.
Bro, this is so genius.
Yeah, this is pretty cool, right?
Did you understand?
Yeah, like, he just looked at p minus 1 factorial to the power of q, and he's like,
Alright, do you guys have any questions?
That's definitely this set.
Any questions?
There's like a whole
Can I have the
field
video
of